All right. Good morning, you 4C students. So I would like to send you this file because I think the students will on Monday ask you to work on some of it, and so I would like to go over the solution of it. They have exam on Tuesday, so I think they will be kind of excited to ask you questions. Now, the exam is not going to cover Newton's law. It's going to cover primarily projectile motion, and some of you already have seen that with some of the students because they are asking that for you. But let me solve even the part that includes Newton's law, and so that in case they ask you, you are okay with it. But basically, according to Newton's second law, does the direction of the net force always equal the direction of the acceleration? So this is correct. So the net force, wait a second, give a notation. So according to Newton's second law, the net force is equal to the product of inertial mass with acceleration, which means the direction of this vector equals the direction of this vector. Mark how that applies. So sometimes the direction of the net force will determine the direction of the acceleration. So sometimes it's not good. So mass is always a positive number, right? So the direction is always the same. Yes, the direction of the net force will determine the direction of the acceleration vector. So this is good. It depends on the number of forces applying. No, it doesn't. No, the direction of no. So B seems to be the good one. When constructing a free body diagram, why is it a good idea to choose your coordinate system so that the motion of an object is along one of the axes? Well, the reason is when you have several forces, right, acting on something. So you have several forces. Um, you could come up and put your axes like this, y and x like that, right? You could do that. But then you have to project this here, have to project this there, so you have a lot of projection going on. Whereas, and once you project here, so let's say the direction of motion is this way, right? So you have all these different forces, right? Have one, two, and three, and they combine in such a way the direction of motion is this. It means your acceleration is either this direction or that direction, if you think about in a straight line. So if you choose an axis that is coinciding with the direction of motion, right, like this, so once you find your net, you only need to worry about um, the projections along these axes. You don't need to worry about y if you want to deal with acceleration, because the net of forces in my x-axis is going to be equal to m times the acceleration, and that's the only one you have. That's the final acceleration you're going to be in x, and then the problem is resolved. Whereas if you had chosen different axes, then you would have a component of your acceleration in y and another component in x. So you have two of them to deal with. And and certainly once you've done that, if you add them up as a vector, you would have the one that you would, determined had you set one of the axes along the direction of motion. So if the motion of an object is only along one axis, then the acceleration is not zero along, no, the acceleration is zero along the other axis. If the motion of an object is only along one axis, then the acceleration is zero along the other axis. This is good. The net force along those axes must therefore equal 0. That's good too. Define the coordinate system such as the motion is in one direction is done purely to be, If the motion of an object is only along one axis, then the acceleration is 0 along, no. Okay, Adam drops a ball from the top of a building. At the same time, Bob throws a ball horizontally in the same location. So this is the concept of projectile motion. So you have the top of a building, right? Top of a building, and then Adam dropped the ball like this, horizontal, just drop, initial velocity 0 in the y direction, right? And Bob throws the ball horizontally, so it goes like this. This is Bob, this is Adam. From the same location, which ball hits the ground first? And then you have to neglect air resistance. So if you ignore air resistance, these two balls are going to fall on the ground if they are thrown at the same moment, right? They are hitting the ground at the same time. So the time it takes the ball to go from here to here is the same time that take Adam's rock to go from here to here. Time is the same. Why? Well, if you think about the projectile motion, what I tell the students is to divide the motion in two components. So we have an x component and you have a y component. The x component is one there is no acceleration involved. There are no forces. If you are ignoring air resistance, there are no forces. And the only basic equation is equal x is equal vt. And v is projected vx. When you do projectile motion, whatever initial velocity is given, you gotta project it in the x direction and in the y. No. And in the y direction. So we have to add these two components to have your initial velocity. So your v naught x is this one over here. And in y, you have also some initial velocity projected in y. So in both cases, if you think, Adam dropped the ball. So for Adam, this is 0. And for Bob, the ball velocity projected in y is 0, right? Because this angle is 90 degrees. The angle, it's horizontal velocity does with the y-axis is an angle of 90 degrees. Cosine of 90 is 0. So then go to the options. It depends on how fast the ball falls. No, I don't know. They both hit, so B is good. An object travels with a constant acceleration of 10 seconds. So acceleration constant for 10 seconds. So it's a constant number. The vectors in the figure below represent the final and initial velocities. Determine the average acceleration. So definition of average acceleration is always final velocity minus initial velocity over the time. So that's it. That's the only thing you do. Now we have to remember that your final velocity must be given as projections in the Cartesian axis, right? So final velocity, which is this fellow over here, is equal to 20 cosine of 30 in the x direction plus 20 sine of 30 in the y direction, and v initial is equal to so your projected in x is going to be a positive value, 20 um, cosine of this angle, cosine of 60, right? Cosine of 60, this angle is 60 because you are projected in x. So I would write cosine of 60, but I could also write sine of 30. So they're going to be crazy with that, but I hope you can follow me here. And the projection in y is going to be negative. So this vector is being projected in the negative direction, and that is given by 20 cosine of 30 in the y direction. And then you can operate here on the top. So you take these numbers and then you subtract from these numbers and make sure this negative sign is going to be applied on the Vy. So this is going to be negative and this is going to be positive, right? So this is going to end up being positive. You're adding that component in y and you're subtracting this component in x, and then you have your acceleration. So once you have your acceleration as given as something in the x direction plus something else in the y direction, that's your solution. Yeah, because sometimes I might ask for the magnitude of your acceleration, and so the magnitude of the acceleration is given by this much, right? Then you have to finalize that. And if you wanted the direction of it, the direction tangent is equal arc, whose ratio is given by ay over ax, and then you have to decide which angle that is. Okay, to go to a coordinate system. So ask me on Monday if you have any question. So determine the net force on an object in question 4, the previous one, if its mass is 10. So this is pretty much F is equal 10 times whatever that acceleration was. And then you're done. Now, projectile motion. They might go over and ask you about this. A soccer ball is kicked with, so given information, and I'm telling them always do the problem like this. You take all the given information and then you write on the side so you know where to go. And the angle is 30 degrees. So pretty much above horizon is this. So this is 30 degrees, right? Above horizon is the same thing as above the horizontal line, right? So it's horizon, it's something. So what are the velocity vectors of the ball when is 1 meter above the ground level? Assume the ball was on the floor, okay? So so we have the angle, we have the direction of your initial velocity, and we want to find, so what do we want to solve for? We want to solve for velocity at 1 meter above the ground. So basically how this projectile motion works. So the ball is kicked from the floor, that is an assumption, and the initial velocity is here. The initial velocity is here with an angle of 30 degrees. And basically the ball is going to go like this. So you have a tangent right here that goes like that. And when the ball is 1 meter right here, you want to find the velocity. Okay, and basically this position is 1 meter, 1 meter, 1 meter. Okay, so we want to find the velocity at this point. So what do we do? Well, the initial velocity, the first thing they should start their analysis is, the first step is, well, my velocity. How does my velocity behave? So I have 25 meters per second with a 30 degrees angle. then it means I do have a v naught x, which is given by 24 cosine of 30, and I have a v naught y, as you can see, is positive, which is 24 sine of 30. So I have those two, right? And then I go to my table on x and y. So my x component and my y component are then given. My x component are, if I need it, right? X positioned at any time is equal to 24 cosine of 30, which is my v naught x times the time. So once I know the time, I can find position. I can find position at any time, right? So this position is a time-dependent position. Is this one here? So and pretty much in x I'm done, and I know my v naught x is going to be the same all over. It doesn't change. So one of the components of my velocity vector that I need at this point location, I already know is my v naught x, which is given by 24 cosine of 30. So what I need to find now is the component of my velocity vector. So how do I figure that? Well, I go to my y-axis, and in my y-axis I have three basic equations. The equation of displacement, y minus y naught v naught y t minus half 9.8 t squared. Oops, what did I do? 9.8, and I'm going to multiply here, times t squared, times t squared. This is times t squared. So that is the displacement. It's interesting because here, so this is v naught I have, the displacement I have. The final displacement is pretty much 1, right? Is 1. That's the final displacement is at 1 meter above the floor, and the initial displacement where the ball was kicked was at the origin, 0. So y final minus y initial is basically 1 meter. That's what we are finding here. Is equal to v naught y, which is 25 sine of 30 times t minus 4.9 t squared. So what basically you're finding here is a solution of time. So your finding time is going to be a certain number of seconds. Okay, you have time as a certain number of seconds. I suspect, I don't know if you have 1 or 2 times. You might have 2 times. We have 2 times, we have 2 velocities. I don't know if that is right, or we have another 1 meter here, right? So we're going to have a v vector like that. We're going to have a v vector like that. The vx for both of them will be the same, except the velocity in y. In this part of the curve, the velocity in y is upward. The velocity in y here is downward. But anyway, so what I'm saying is you're going to find a time, and once you find a time, you can find your velocity. What did I do? You can find your velocity in y. Velocity in y is equal velocity initial in y minus 9.8 time, and then you plug the time here. You have the other component of your velocity, and then you can find velocity vectors of the ball, and then you are done. On a beautiful sunny morning, Taffy Nguyen leaves home and bikes 50 kilometers. Okay, I think you guys did that before, didn't you? Well, let's do it again. On a beautiful sunny morning, Taffy Nguyen leaves home and bikes for 50 kilometers. she bikes 50 kilometers, heading 30 degrees north. So this is pretty much north, south, east, and west. Bikes 50 kilometers north of east, so north of east. So this is 30 degrees, sorry. And she goes a good 50 kilometers, and then she stops and for a water break. And then she turns due south and bike another 25 kilometers. So she goes 25 kilometers here to visit her aunt Kathy. How far from home does the aunt live? So you want to find this displacement here, right? That's the displacement. So you have a vector A, vector B. The best way to deal with this is you write a vector A as being 50 kilometers cosine of 30 plus 50 kilometers sine of 30 in the y direction. So you write any vectors as based on their projections. So vector B in x has nothing, right? But in y is negative 25. So A vector plus B vector, sorry, it's messy. So A vector plus B vector gives your displacement vector. So D is equal to the sum of these two things here. 50 cosine of 30 plus 50 sine of 30 minus 25. All of this in the y direction. But sine of 30 is half, so this is going to be 0. Oh, how interesting. So it's going to stop right here. So how far from home the aunt lives is 50 cosine of 30 in the x due east, basically. For an extra bonus, determine the direction of tap south with respect to hers. Well, it's yes, 50 cosine of 30, right? So that's it. So let me know if something is not clear, and then I can talk to you on a chat room over the weekend. Just let me know, okay? Oh, no.